HLAA vectors, day number 5. Today's topic is the vector product and the mixed product. We'll also talk about applications of both of these concepts. All right, so given two vectors, A and B, their vector product is given by the following. Now we're going to go through a few practical examples utilizing this, so you'll see how we go about that. But that's under the assumption that we define A as the vector in 3 dimensions, A1, A2, A3. So this would be the vector product of two vectors in 3 dimensions. It looks slightly different if we were in 2 dimensions. We would just have B1 and B2 and A1 and A2. The vector product A cross B, this is also referred to as the cross product. So the vector product can be referred to as the cross product. Results in a new vector C, where C is perpendicular to both A and B. I'll explain a little bit more about that in the coming slides. It can also be shown that the magnitude of the cross product of two vectors is equivalent to the product of their two magnitudes times the sine of the angle in between. Okay, we'll talk about the applications of that later on during these notes. Now I am going to post a video also covering the derivation of said formula. So let's go ahead and get to it. Okay, on this slide here, what I'd like to do is cover an example of the vector product, also known as the cross product, of these two 3-dimensional vectors A and B. And then I'd like to talk about what's called the right-hand rule. So let's go ahead and get into it. Okay, so when we work with A crossed with B, what we're doing is we're finding what's called the determinant of this specific matrix. Okay, so I take vector A and I align the components 2, 3, and -1 horizontally like that. That's vector A. Vector B will be 4, -1, and 1. Okay, so the result of a previous product that we called the scalar product, its result was a value, right? A constant. We've already talked about this, but the result of a cross product ends up being a vector. Okay, so we get a resulting vector, which we've called C. Okay, so here's how we go about the mechanics of finding this. We're going to have 3 components to this new vector. Seeing that the two vectors that we're crossing are 3-dimensional and have 3 components themselves. One thing that you want to get used to with regards to the mechanics of this process is based on the orientation of this matrix here, we're always going to take the opposite of whatever we get for our J component. Okay, so just get used to putting a negative there based on the process that we're going to use. Okay, so if I want the I component, what I'm going to do is cross the J and K components. So I'll show you what I mean by that. So if I want the I component, I'm going to work with the J and K components of both vectors. What I'm going to do is I'm going to take, this would be A2 times B3. Okay, so what would that be? That'd be 3 times 1, which is 3, minus A3 times B2, which would be a 1. So our I component for our cross product resultant vector would be 2. Okay, so I'm just ignoring the I component when I'm ignoring the I components, right, of the cross product when I find the resulting I component. Okay, that might have been confusing, but it'll make sense here in a moment. Let's find the J component. Okay, so with the J component, I do the exact same thing, except now I'm working with the components for the, let's see, how do I want to describe that? The I and the K k components, right? So I'm going to take 2 times 1, which is 2, minus -1 times 4, which is -4. So I would get a result of 6 there. Now recall that we're going to have the opposite of that value, so it'll be a -6. Okay, for the k component, I consider the I and j components of my determinant. That would be 2 times -1, which is -2, minus 3 times 4, which is 12. So the k component of our cross product ends up being -14. Okay, so this vector c, which, by the way, is perpendicular to both a and b, could be written in the following form: 2, -6, -14. Okay, so this brings up an interesting topic. This is called the right-hand rule. Okay, so let's say that in 3 dimensions I have this vector A, looks kind of like this, and this vector B looks kind of like that. Well, if I want a vector that's perpendicular to both, you can imagine I'd either have a vector that's coming out of both of those at a right angle upward, or potentially a right angle downward. Okay, so which one would it be? Well, if you were to take your right hand and say put your thumb upward and your middle finger right on vector B, and you rotate all 4 fingers from B to A, your thumb would face upward. So since I've started at B and I've headed toward A, the vector product of B cross A would be that green vector C. Okay, now imagine you take A with your right hand and you cross it with B. Well, clearly if I were to take A and put my right middle finger on A, my thumb would point downward. Right, it would have to point downward as I rotate over to B, and therefore the direction for C in that case would be in the direction of that red vector. Hopefully that made sense. But you always use your right hand, always put your middle finger on the vector you're starting with and rotate it toward the vector you're headed or crossing it with. And whichever direction your thumb points, using your right hand, that'll be the direction of that normal vector, right? That resultant. That's the right hand rule. All right, let's continue. Okay, some other properties of the vector product, 1 through 4 there. Those you're going to prove in your homework, so have fun with that. That's cool. Let's look at an example. And this example here actually is going to take us back to our chapter on proofs, which was first semester. So here we have what's called an if and only if proof. Okay, if you ever get an if and only if proof, what that means is you have to prove this in 2 directions. All right, so that means show that 2 non-zero vectors A and B are parallel if and only if A cross B equals 0. Okay, so what I'm going to do is I'm going to start with the red as an assumption and prove the blue. And then the other way around, I'm going to start with the blue and I'm going to prove the red. Okay, so let's start in the forward direction, right? We refer to this as the forward direction. Okay, so what is the assumption that we're looking at? Well, we're assuming that A and B are parallel. Well, what I can do is I can let A equal the vector. Let's go 2 dimensions to keep it simple. A1, A2. And B equal the vector B1, B2. Okay, if A is parallel to B, right, that's the assumption I'm able to make, then what I would know is that A is equal to K times B, okay, which tells me that A1, A2 is equal to some constant k times B1, B2. That tells me that they're headed in the same direction. Okay, thus, A1 is equal to k times B1, and A2 is equal to k times B2. Okay, now, here we go. Now that we know what we can assume, we can go ahead and prove this. Therefore, A cross B, right, if I were to take A cross B, which would be A1, A2, excuse me, A1, A2, B1, B2, would be equal to A1 times B2 minus A2 times B1. Okay, so all I did was I used our example from the previous slide, and I took A1 times B2 minus A2 times B1. Okay, and what that's going to end up giving me is an expression that I can now work with. I know that A1 equals k times B1. Okay, so really A1 I can sub in with a k times B1. Okay, I sub that in. Minus A2, which is equal to k times B2 times B1. Okay, so I subbed in for A2 a k times B2. Now check that out. Those are equivalent expressions. I'm subtracting, and therefore the cross product is 0. So I can go ahead and say, hey, I proved it. Okay, so I proved the forward direction. Now let's go with the backward direction. And let's assume, again, that A is equal to A1, A2, and B is equal to B1, B2. Okay. And that A cross B is equal to 0. Okay, so now we go. All right, so A cross B, as we know, is A1, B2 minus A2, B1. And what we're doing is we're setting that equal to 0. Okay, if that's true, then that means that A1, B2 is equal to A2, B1. And thus, by definition, what we can do is we can say that B2 over B1 is equal to A2 over A1. And since B2 over B1 is equal to the slope of B, and A2 over A1 is equal to the slope of A, then the slope of B is equal to the slope of A. Oops, I should put that in lowercase letters. Thus, A is parallel to B. Boom, got it. Okay, that's an example of a two-way proof, if and only if. All right, let's continue. Okay, so we've talked about the vector product. We've talked about the scalar product. Now we're going to talk about one of the more interesting examples, which has application later on. It's called the mixed product. The mixed product is an operation with three vectors, combining both the vector and scalar product. Okay, so let's take two vectors, A and B, let's cross them, right? Find their vector product. And then take the resulting vector and do the scalar product with a third vector. So down below I have a general case, right? Example, given the vectors below, find the mixed product, A cross B, dotted with C. Okay, and of course the parentheses are there for order of operations. In terms of the components of the three vectors, so I've got A is A1, A2, A3, B is B1, B2, B3, and C likewise. So we know that A crossed with B is the following vector. All right, we've got this here. A crossed with B dotted with C is going to be a whole huge mess, right? but it's going to give us a nice, well, maybe not nice, I don't know, however you want to imagine this. What we're going to do is take A2, B3, C1 minus A3, B2, C1. We're going to duplicate that. A3, B1, C1 minus A1, B3, C, excuse me, that should be C2. Okay, and then A1, B2, C3 minus A2, B1, C3. Okay, so you can kind of see where we're headed with this. We're going to do some practical work with this, with actual numbers here in a moment. So let's get to it. Okay, so before we get into the application, or excuse me, the practical use of each of these, what I want to do is I want to talk about the applications of these various products. So the vector product, right, A cross B, has some important conceptual understanding to it, right? So if I take A and I cross it with B, okay, here's A, here's B, A, B, and I cross them, what I get is the resulting vector C, right? And C is perpendicular to both A and B. All right, and using the right-hand rule, I can determine whether that's headed one direction or the other. Okay, cool. What's interesting about the magnitude of A cross B, right? So if I take the magnitude of C, which is A cross B, right? So recall this is A cross B. If I took the magnitude of that new vector, and I'll prove this in a different video, that actually finds us the area of the parallelogram that would be formed by vectors A and B. Really interesting. Okay, now if I took half of that, right, if I took half of A crossed with B, which would be half of the resulting vector, magnitude of the resulting vector C, same thing, divided by 2, that actually finds me the area of this triangle. It's really cool, pretty awesome deal. Okay, we're going to get to some examples with that momentarily. Oops, okay, I'll just continue to write here. The mixed product has a really cool application as well. Okay, so the mixed product works for us in 3 dimensions, while the vector product works for us in 2 dimensions. So the vector product finds this area when we take its magnitude, okay? The mixed product will find us volume. Now, one thing that you want to be careful for here, okay, when I do a cross product like I do here, this ends up being magnitude, right? So a cross product is a resultant vector. With a vector, if you have absolute values, that's magnitude. Down here, when I do a dot product or a scalar product, these bars here don't mean magnitude, they mean absolute value. And those two things mean the same thing, right? Magnitude and absolute value. But when I'm working with just a constant, that'll be the absolute value. Okay, so let's talk about what this would mean in the context of volume here. Okay, so I've got A, B, and C. Okay, so here's A and here's B. And just so we don't mistake C for the cross product of A and B, I'm going to call C just some other vector. Okay, when I dot these two, right, A crossed with B, and this third vector C, what happens, I'll get a constant, right? And that constant might be negative or it might be positive. Well, the absolute value of that constant comes out to be the volume of the, whatever we call this, the parallelepiped, whatever. It's a prism, right? So let's visualize this prism. Okay. So I would find the parallelogram projected by A and B. And then what I would do is you can kind of see this take shape in the following way. Okay, and here will be your prism. Okay, so that'd be the prism you're finding the volume of. It's really actually an amazing thing. So the mixed product does some pretty cool work for you when you take the absolute value of its result. Okay, let's look at a practical example on the next slide. Okay, so for this example, I'm going to find the volume of the prism enclosed by those vectors. Now, when I find this volume, I can do it in a number of ways. I could take the absolute value of A crossed B dotted with C, or I could take the absolute value of B crossed with A dotted with C, or I could, and I'm not going to write all the options out, but I could take the absolute value of B crossed with C dotted with A, right? And all the other possibilities there, which I think there's only a couple more. Okay, so let's get into this. Let's take A and cross it with B. I'm just going to use the first option here. Okay, I'm going to cross A and B. So I'm going to take the determinant of this matrix here, -1, +1, -2, and 2, 1, -3. That'll be A crossed with B. Okay, so I'm going to get an I component, the opposite of my J component, and my K component. Let's see what we get. Alright, so for my I component, I cover up the i's. I take 1 times a -3 minus -2 times 1. So that's -3 minus a -2. So it's -3 plus 2, which is a -1. There's my I component. My J component, I cover up J. I get a +3 minus a -4, which gives me 7. Okay, +3 minus a -4. Got it. Okay, K component, cover this up. -1 minus 2. That's a -3. Okay, so A crossed with B is equal to the following vector: -1, -7, -3. Okay, what is C? Well, C is given above. C will be 1, -2, and 1. Now, let's go ahead and do the work to find the volume. The volume will be the absolute value of A crossed with B dotted with C. Well, let's find A crossed B. We have that, and dotted with C. Okay, so that'll be -1, -7, -3, dotted with 1, -2, and 1. Okay, the result of that comes out to be -1 times 1. Okay, this is the scalar product of two vectors, right? Scalar product. Then we're going to add -2 times -7 and add -3 times 1, which gives us a result of 10. So that's the result of A crossed with B dotted with C. If I took the absolute value of that, well, nothing changes. And so the volume of this particular prism is 10 cubic units. Okay, let's look at a unique example of something very similar. Show that the following vectors are coplanar. Now, to show that three vectors are coplanar, we could show, and the hint is given here, that the volume of the prism is 0. That would mean that all three vectors are on the same plane. Okay, so let's work with A cross B. Okay, so we'll do the same thing we just did above, A crossed with B. Set up the determinant of this 2 by 3 matrix, 1, -2, -4, and -1, 1, and 1. Okay, so A crossed with B. Let's set up the components and then we'll do the algebra. Okay, so for component I, I'd take -2 minus a -4. It gives me a +2. It's good, I like that. Cover up the J. I get 1 minus 4. That's a negative 3. Cover up the k. I get 1 minus 2, which is a negative 1. Okay, so I get, for A cross B, I get a 2, I get a 3, I get a negative 1. Okay, we know C. C is 2, negative 1, 1. So let's do our work. Our goal here, you can pause the video if you want, is to figure out a way, well, we're not figuring out a way, we're actually showing that A crossed with B dotted with C has to equal 0, right? So show that the volume is 0. We're hoping that this result comes out to be so. All right, so I'm going to dot these 2, 2, 3, negative 1, dotting it with 2, negative 1, 1. So I get 4 minus 3 minus 1. And look at that. Therefore, of course, if I took the absolute value of this, right, which would be the volume, we would get the absolute value of 0, which of course shows us that the volume is 0. So since the volume of the prism is 0, the 3 vectors A, B, and C are coplanar. All right, guys, let's do one more slide. Okay, this last slide, it's really interesting. It's asking us to find the volume of a triangular pyramid with the vertices A, B, C, and D. Okay, so a triangular pyramid, what does that look like? Well, that's a pyramid, right, that has a triangular base, right? So it'll likely look something like this. Okay, so now I want you to think about how this would relate to the mixed product, right? So let's say this is A and this is B. And honestly, like, I don't care which one's which, but let's say this vector is C. All right, so let's relate to this to what the mixed product gives us. Right? So if I took A, crossed it with B, dotted it with C, right, and took the absolute value of the result, that would give me the volume, right? This would give me the volume of the following. Oh boy, how am I going to do this? This is not an easy one to. Okay, this is coming together. Okay. How do I want to do that? Oh yeah, like this. Let's go like that. Okay, so imagine, right, that prism there. That would give me that volume. Okay, so you got to know a couple of things here. There's a special formula, right? So in geometry, the volume of a prism is the area of the base times the height, right? So the area of the base would be like this parallelogram here, right? Or whatever the quadrilateral might be. Okay, so that'd be the area of the base. The height would be whatever the altitude is, right? So straight line distance from top to bottom, that'd be your height. Okay, now when I take this and I turn it into a pyramid, if this were a rectangular based pyramid, right, or a quadrilateral based pyramid, and I kept those the same, the volume of a pyramid is actually 1/3 of the volume of the prism with the same base. Okay, so, but what we've done here is we've not made this a parallelogram as its base, we made a triangle. So we've actually adapted this to be 1/3 times the area of the base. The area of the base is going to change from a parallelogram to half of the parallelogram, right? Which is a triangle times the height. Okay, so what do we got here, right? So what we have essentially is 1/3, okay, times 1/2 times the mixed product. Okay, so what we're going to do is we're going to find 1/6 of the mixed product and then the absolute value of that. So let's see if we have to use the absolute value here. Okay, so mixed product. Now this is interesting. Like, do I have to use A and B, right, and C, or do I have to use A, B, and D, or does it matter? It doesn't matter. Okay, what I'm going to do is I'm going to define, and actually let's plot this thing out. Okay, I'm going to try to do this to the best of my ability. Go 3 dimensions here. Here's the X, here's the Y, here's the Z. Okay, so let's plot A first. A is right 1, forward 2, down 1. So right 1, forward 1, 2, down 1. So it's like below the XY plane. There's A. A is the point 1, 2, -1. Okay. All right, how about B? We'll put B in blue. That's 2 to the right and 3 in the Y direction. So 1, 2, and 1, 2, 3. There's B. So B lies above A by 1 unit, and a couple of units in a different direction as well. Okay. All right, so there's A and B. Let's plot C. C is left 3. 1, 2, 3. In the Y direction, 1, and up 1. Okay, so there's C. So C is 1 unit above B in the Z axis. There's C. -3, 1, 1. Okay, now D. D is 0 in the X direction. Let's go -1, 2, 3, 4 in the Y direction, and up 5. 1, 2, 3, 4, 5. There's D. 0, -4, and 5. Okay, so let's take a look at this triangular pyramid. It's going to be kind of difficult to imagine here, but I'm trying the best I can. I'm getting tired. And this is the side we can't see. Okay, so there's your weird triangular, oops, I should draw that edge. There we go. Okay, so there's our weird triangular pyramid. So what I'm going to do is I'm going to take the vector from A to B, and I'm going to cross that with the vector from A to C. And I'm going to do that first, and I'm going to dot that with the vector from A to D. Now it's really important, right? It's actually really important that you know that A is like that origin point, right? So the 2 vectors that you cross come out of A, and the 3rd vector that you dot it with also comes out of A. Okay, so let's go ahead and find this thing here, and then we'll multiply by 1/6 and take the absolute value, and we should be good to go. All right, so let's find AB and cross it with AC. All right, so what is AB? AB. Well, AB would be all the points of B minus the points of A. So that's 2 minus 1. Okay, so 2 minus 1 is 1. 3 minus 2 is 1. 0 minus -1 is 1. Okay, so I get AB is 1, 1, 1. AC is going to be all the points of C minus the points of A. So -3 minus 1 is a -4. Then I get a -1 and a +2. Okay, now I'm going to skip the color coordination here for a moment just so I can save some time. And I'm going to cross AB and AC. Now you can check the math on the back end here and kind of do this on your own. But AB crossed with AC ends up being, let's see, 3, -6, 3. Okay, cool. So that's AB crossed with AC. Now the other thing I need is AD. All right, so AD, very similarly, I'm going to take the points of D minus the points of A. AD comes out to be -1, -1, excuse me, -6 and 6. Okay, so now I'm going to take these two vectors, AB crossed with AC, and of course I'm going to dot them together. All right, so that's going to be AB crossed with AC dotted with AD will equal 3, -6, 3, and -1, -6, 6. The result of that ends up being -3 and 36 and 18. Looks like I don't have to use the absolute value here, but I think that comes out to be 51. Okay, so then the absolute value of that is still 51, and therefore the volume of the parallelogram, prism, would be 51. Now I want 1/6 of that, so the volume of this particular triangular pyramid would be 51 times 1/6, which comes out to be 17 halves, or 8.5 units cubed. All right, guys, that's it for the vector product and mixed product, some cool application problems. We will see you guys in the next video.